So I'm here to talk today about power to gas and hydrogen energy storage for a 100% renewable future. Thank you so much for the invitation to speak to you. I want to begin with some notes of introduction and background. I come from the University of California, Irvine, which has several points of pride that you see on this diagram here. We're the #8 public university. I think that puts us several slots behind UC Davis, unfortunately. But anyways, #8's not bad. We also have been doing a lot with regard to first in family admissions and supporting them throughout their college career so that they end up graduating with their degree and getting good jobs. I'm very proud of what we've been doing in the last 10 years, especially to promote that. And we've been recognized by the New York Times for doing this, for doing the most for the American dream. That's pretty cool. I think one of the coolest things, though, is associated with our program, and that is the Sierra Magazine rating of UCI as one of the top 10 cool schools. A little play on words there, but it's mainly for adopting within the infrastructure of the university, but also accomplishing research on sustainability, okay? And every year that we've applied for this award, something that we did at APEP was included, like some research project or some demonstration project that we were doing was included in our application. And in 2020, the last time this rating was given, we were the coolest school. And it's the 4th time that we've been the coolest one in the United States. Anyways, it's a pretty cool award. And what about the Advanced Power and Energy Program? We've been very fortunate to work with so many outstanding colleagues in the universities and industries to accomplish world-leading research in many different areas. And I'm just going to show a few pictures of background information here. We introduced this idea about 15 years ago, the Transmission Integrated Grid Energy Resource, or a TIGER station, which is the idea of integrating very large fuel cell systems within the transmission system of a utility grid network. And these have fortunately, over the last couple of years, actually been applied in many places around the world. We've always tried to integrate fuel cells and hydrogen systems with renewable power, and we've done this since the founding of the National Fuel Cell Research Center here at UCI. We introduced this idea of tri-generation of hydrogen heat and power using a high temperature fuel cell. And we were fortunate to work with Air Products and Fuel Cell Energy to demonstrate this at using biogas at the Orange County Sanitation District. We've done a lot of research on fuel cell gas turbine hybrid systems. And this is a picture of one that we actually demonstrated in our facilities. We've been spending a lot of time lately doing work on microgrids, and we developed a generic microgrid controller. And we have quite a microgrid on our own campus with 4.5 megawatts of solar, hydrogen production and injection into pipelines, battery energy storage systems, etc. We also have a fueling station on our campus and have had one since 2002. It's not only fueling our fleet of vehicles, which we actually no longer have, but it did that for many years. We were testing fuel cell vehicles together with Toyota. But now it's a publicly available station. We've done a lot of research on fuel cells applied to trains and locomotives, one of the applications that's pretty difficult to make zero emissions otherwise. We've done a lot of work on solid oxide fuel cells, but also now solid oxide electrolysis systems. We've introduced to our campus microgrid a power to gas to power project, where we take our excess renewable energy when it's available, and we put that renewable energy through an electrolyzer that makes hydrogen, and that hydrogen is injected into our natural gas system, and that goes to our natural gas combined cycle plant, partially decarbonizing that, essentially making our, by power to gas, making our solar dispatchable. We've also had a long history of studying low emissions in gas turbines, and have more recently been applying hydrogen technologies to these gas turbines and other things. You can see here, this is an appliance in which we are introducing hydrogen as a fuel. Many years ago, it was about 2013 or so, 7 years ago, we started working with Microsoft to consider fuel cells for data centers. I'm not going to be able to talk too much about that today, but that's been an exciting area for us. We've been doing power to gas research since probably 1999 or so, where we take renewable energy and we put it through electrolyzers and make hydrogen. And we have a fuel cell bus that's been in continuous operation on our campus for the last 3 years. Since we have a hydrogen fueling station on our campus, we can actually refuel it directly. And it's one of the buses that is in our completely zero emissions fleet. The rest of the buses are battery electric, and the fuel cell bus is the largest one. It can carry the most passengers, and it also goes on the longest route because of the features of hydrogen, which enable larger payload and longer range. Now, this fuel cell gas turbine system that we developed with Siemens was the world's first hybrid fuel cell gas turbine system. This tri-generation system was the first high temperature fuel cell tri-generating hydrogen heat and power in the world. This refueling station on our campus is the most popular station in the United States. This fuel cell bus was the first to be used in regular operation and continuously over the last 3 years in any university in the US. This was the world's first powering of data with direct DC from fuel cells, data centers with direct DC from fuel cells. This was the first in the US power to gas to power demonstration done on our campus. There were other countries that beat us though. This is the first generic microgrid controller in the US, and all of the gas turbines on aircraft and in power plants are using some technology that came out of our low emission gas turbine work in our lab. So we're pretty proud of this. Hopefully you can see some new things appear over the coming years, but we're pretty proud of all of these accomplishments. We're also very fortunate to recently have hired some new faculty members that we are working with and that are part of our Advanced Power and Energy program. First is Professor Irina Zenyak. She's an associate professor with tenure in chemical and biomolecular and mechanical and aerospace engineering here, and she's the associate director of the National Fuel Cell Research Center. She's outstanding and is primarily a proton exchange membrane fuel cell expert, but in particular is famous for her X-ray operando imaging of proton exchange membrane fuel cells. But she's doing lots of other research that is associated with how fuel cells degrade or how we can understand mechanisms for platinum dissolution with in situ measurements as the degradation is occurring. And then she also makes her own MEAs, trying to improve them and to make them more durable and long lasting. We also were able to hire recently as a chancellor's professor, Plummen Atonisoff, professor in chemical and biomolecular engineering and material science and engineering, and also chemistry. And you can see he has some very fundamental contributions that he makes to electrocatalysts, in particular the structured platinum alloys, and in platinum group free metal catalysts. His group is really famous for designing for structure and reactivity at various scales, at a hierarchy of scales. And you can see that he has relationships also with many industries like Toyota, Bosch, but also laboratories like the US Department of Energy and Los Alamos that he continues to work with here at UCI. And then most recently, we were able to hire Professor Voja Stamenkovic as a professor in chemical and biomolecular engineering, but also as the director of our new HORIBA Institute for Mobility and Connectivity. He's actually very famous for electrocatalysis, but applied to all sorts of electrochemical conversion devices like electrolyzers, fuel cells, batteries, and in particular, the bottom-up design of these materials, from the very fundamentals, electrochemical interfaces and the engineering of them, and then things that are like way above my head here. I don't even know what he's talking about here with altered functionality. Maybe some of you know. Anyways, I wanted to make sure you guys knew something about the background and introduction, and also some exciting new hires associated with advanced power and energy, and especially electrochemical energy conversion at UCI. So now I'd like to begin the seminar part of this discussion. And I want to begin by thinking of the Earth energy balance and a very simple first law of thermodynamics analysis that draws a control volume around the Earth and considers energy in, which is coming to us from solar radiation. There's some solar radiation that's reflected, and there's some, of course, that the Earth radiates back out to space. And these are essentially all the energy units that are crossing this control volume boundary. So it's a very simple energy balance. And most people think that I'm going to talk about climate change at this point, but I'm not gonna. I'm going to think rather about primary energy on Earth. And I want you to think about the concept of all of this, except for nuclear, coming from the sun. As a matter of fact, the fossil fuels that we use in society today have come from the power of the sun, which made plants and animal life possible. But after they died, the heat and pressure and millions to hundreds of millions of years produced this fossil fuel that we use today. That's a very long time scale, but this is naturally done on Earth from the power of the sun. Now, this is such a long time scale that I have to draw a crosshatch through this one because all of the other primary energy forms on Earth that I'm going to talk about have much shorter time frames in which they are naturally replenished on Earth. Like, for example, the bioenergy sources, corn, trees, grass, these sorts of things are produced by the power of the sun on the order of months to years. So we can make things like ethanol, biogas, biomass resources. We also have hydropower, which takes order of magnitude months or weeks to produce. The sun energy evaporates the water, forms it into clouds. The clouds move over the mountains and they drop their rain and they fill the lakes. These sorts of things from the sun. And the wind power that we have also comes from the sun, creating those pressure gradients that drive the wind. And then, of course, solar power, which during the day, the instant you use a unit of it up, you have another unit coming at you. It's quite obvious that sustainability requires the conversion of these resources at the same rate at which they are naturally replenished on Earth. That's just the fundamental energy balance that we must live under. Okay, so we have to think about the time scales for naturally replenishing things on Earth. Now, I add this without externalities because it isn't just the availability of the primary energy resource that must match our use of these primary energy resources, but we got to be concerned about externalities as well. And if we look at a relative timescale of humans on Earth, okay, the way that we are using our current fossil fuels is quite obviously not sustainable. It appears as a delta function over the course of human history. It's quite obviously not sustainable. And we must then use other forms all of those other forms that are more rapidly, naturally replenished on Earth. And fortunately, solar and wind prices, because of policy and because of the dramatic increase in their use throughout the world, the prices have dropped dramatically, enabling us to envision a world in the future where all primary energy comes from these kinds of resources. These are actually the cheapest energy sources available today. Cheaper than natural gas plants, cheaper than coal plants. So these are becoming ubiquitous. But it's not just those primary sources of energy. Unfortunately, we must think about these externalities that I mentioned earlier. Because if we make renewable hydrogen, or if we make batteries and we have externalities associated with that, if we burn hydrogen in combustion systems and we create criteria pollutant emissions, we have to be concerned about that as well, even if it's all renewable. Okay? And I want to suggest that we must not lose our focus to address criteria pollutant emissions at the same time that we address greenhouse gas emissions and other externalities. These are today creating serious health and air quality consequences, even in the most sophisticated and advanced and successful economies of the world, like right here in Los Angeles or in Beijing. In addition, we have other externalities associated with our use of fossil fuels, especially like resource recovery damage or regional resource depletion, creating these geopolitical conflicts. And of course, what I presented earlier, it's not sustainable to keep doing this. So I hope I've convinced you, and I hope you, together with me, can convince all of society that we must go to a 100% renewable and zero emissions power generation. And it's popular today for us to think about this. The main strategy that the public knows about is that we could make 100% of our power from renewable sources like solar, wind, and geothermal. They think that also we can electrify all end uses and then use batteries to handle the intermittency on the grid and for end uses like automobiles. And this is quite popular and easy to understand, and also visually reinforced by what we see happening in our own homes. Many of us with battery electric vehicles, many of us with solar on the roof, some of us with batteries in our garage. Or you can see this in your neighborhood. So this is the popular thinking. And then people who think a step deeper about what else we might need sometimes argue against hydrogen and fuel cells. They say things like this: most hydrogen today is made from fossil fuels, natural gas. Making hydrogen from water and electricity is less efficient than charging a battery. Making electricity from hydrogen in a fuel cell is less efficient than a battery, so that the round-trip efficiency is lower than a battery. And hydrogen is difficult to store and move around in society. This is not only popular, it's actually being advanced by some very influential people that I admire, like this guy. He makes these arguments against hydrogen and fuel cells. And what's interesting is I agree actually with most of this. It's quite close to technically accurate. The problem is it's subtly untruthful. And it doesn't tell the whole story. Just a few modifications of this might make it completely agreeable from my perspective. We can't electrify all end uses. There are some that will require a fuel, some that will require a reducing gas, some that will require chemicals. We also can use batteries on the grid, and we're using them already today to handle some of the intermittency and for some end uses. For example, light-duty vehicles. They may be primarily battery electric vehicles for the efficiency reason that you see below. And interestingly, batteries are more efficient in their round trip efficiency, except for long duration storage applications where hydrogen energy storage could even be more efficient. So these small modifications, but significant modifications, are important for us to understand so that we have the whole story. So let me tell you, let me just give you some of our recent research results that are related to how we might achieve a 100% renewable and zero emissions grid and full economy using the hydrogen vector. I'm showing here a dynamic simulation for a whole year of the California electric grid every hour by hour, going from January 1st to December 31st. Okay, and I'm showing here the residual load for a case in which we have installed 37 gigawatts of solar capacity and 80 gigawatts of wind capacity. So this is a very wind dominant case. We've looked at other cases too, but this is a wind dominant case. And with this sort of installed capacity and the dynamics of the solar and dynamics of the wind throughout the state, in various locations throughout the state, we can actually figure out every hour when we will have a deficit of wind and solar power. That's what all of the red data shows over here, okay, compared to the cases, hours, right, when we have a surplus of solar and wind power compared to the demand on the California grid. Okay, the good news is that if we install this amount of solar and wind capacity and the dynamics are the same as they were in 2016, that we can make it through the year on an energy basis. As a matter of fact, if you integrate under the curve of all of these deficits, okay, they're actually less energy than if you integrate under the curve of all of these surpluses. So we can even curtail some of this surplus and make it through the year. So the only thing we need to do now is we need to move it around in society and move it around over time. So how do we do that today? Today we do that using our pumped hydro system. And on an electricity equivalent basis, this is how big it is. If we turned all the pumps on at once, we'd have about 9 gigawatts of electric power generation that we would draw. And if all the lakes were filled and could release their energy through the turbines and make electricity, this is how much electric energy they would make. That's the size of this rectangle. So one thing that's apparent is that it's not big enough in either its power rating or its energy capacity to move all of this around. We would have to basically only, if all the lakes were empty every day, we could only capture up to 9 gigawatts of this surplus. So we have to curtail everything below here. Some people think that we could install battery electric vehicles and use them on the grid to help with this. And maybe they can move a lot of this. What do you think? You think it can move a lot of this? Well, how about if we made all 21 million of the light duty and medium duty vehicles, battery electric vehicles, and we use them only for charging and discharging on the grid to help with moving this around? Well, this is how big it would be if each one was equivalent to a Nissan Leaf battery of 62 kilowatt hours. Well, as you can see, it would have quite a large power rating, but not very much energy. Only about 4 hours of energy would it be able to store at this power level. So it could help perhaps with daily shifting of a little bit of that energy. And this would be a good idea, right? Vehicle to grid and grid to vehicle connections for moving some energy around in society is a good thing. But it really is a tiny amount in comparison to what the grid would need to become 100% renewable. And we also want to use these cars for driving, right? Okay, so we can't use them only for storage on the grid. So what do we do today to make our highly renewable grid dispatchable, reliable? We use the natural gas system. We use natural gas fired power plants, and we dynamically dispatch them to complement the sun and wind. We also use the gas system to store seasonal amounts of energy. So what if we converted that to renewable hydrogen produced from this surplus, right, and moved it around in society to meet these deficits? This is how big that would be. Converting the existing, not building any new, just converting the existing natural gas storage facilities in California to renewable hydrogen would have a magnitude of power associated with making that electricity, making that renewable hydrogen from this electricity would have a power rating of almost 50 gigawatts. Okay, so you can see it could absorb almost all of these surpluses, and it has an energy amount that is far greater than our pumped hydro system and far greater than even using all 21 million of these EVs. It's the only option that we have that's large enough to take a seasonal amount of energy when it's available as a surplus in the summer, in this particular case, and move it to the fall and winter. Hydrogen energy storage, using the existing natural gas system converted to hydrogen, is the only resource that's big enough. The batteries, I think, will never be big enough to handle this sort of seasonal energy storage. In addition, I had a graduate student, Nuria, here, look at whether or not we could make a world energy demand 100% renewable. And we looked at various continents, as you see here, and assumed various distributions of solar and wind, various contributions from solar and wind. So in Africa, it was a solar dominant case. In Asia, a 50-50 split, etc. And we looked at the dynamics, again, hour by hour dynamics of solar and wind, and hour by hour demand dynamics. And we determined how big the storage facilities would have to be just to make it through the year. And what you can see here is on a worldwide basis, we'd need 20,000 terawatt hours of energy storage to make it through the year on sun and wind power. Now, this might be a little bit larger than we would need because we won't do everything from sun and wind. We'll have some geothermal, we'll have some nuclear, etc. But this is just to get the order of magnitude. And with this order of magnitude, what if we built a lithium-ion battery energy storage system to actually store this amount of energy? If we tried to just use lithium-ion batteries, the very best batteries in the world, lithium-ion batteries, we would need 3,000 megatons, more than 3,000 megatons of lithium, and more than 25,800 megatons of cobalt. And if you look at the resources that are available all around the world, okay, for these compounds, we see that the world only has 53 megatons of lithium and only 25 megatons if we mine it terrestrially. And if we mine the ocean floor for cobalt, we can get another 120 megatons. It's pretty obvious that lithium-ion batteries, at least, could never be built at this magnitude. We don't have enough lithium and cobalt on Earth. It's orders of magnitude less lithium, cobalt, and cobalt than we have on Earth. In addition, more than 60% of the cobalt comes from the Democratic Republic of Congo with poor labor laws and poor international relations. So we should use the precious lithium and cobalt resources for those applications where it can make the biggest difference and be sustainable in meeting those demands, like we do today with cell phones and like we do today with light duty vehicles and things like that. But for grid scale storage, we don't have enough lithium or cobalt in the world. In addition, when we measure lithium-ion battery performance applied to our utility grid network, we find something quite unusual. Maybe you haven't heard about this. It's that this round trip efficiency argument for using batteries instead of hydrogen energy storage, it ends up showing that the average round trip efficiency, so this is what we're plotting here, the average round trip efficiency versus capacity factor for all of the battery energy storage systems that have been installed under the self-generation incentive program in the state of California. So these are actual utility installations that have been installed on the in the California grid. And what we see is that the average round trip efficiency is like 60%. And this was surprising to me because we measure batteries in our laboratory and we get greater than 90% round trip efficiency. We know that when you put these in utility applications, that you have to add transformer losses, you have to add converter and inverter losses and things like that, but they should never add up to something this low with regard to round trip efficiency. And as a matter of fact, the Itron, which made these measurements, okay, they measured all the cooling system losses, all the transformer inverting and converting losses, and they do not lead to this low an average round trip efficiency. What is leading to this low efficiency? Itron doesn't say, E3 doesn't say in this report, okay, but we know what it is. It is self-discharge. Self-discharge is the main culprit that leads to low round trip efficiency in battery utility applications. How do we know this? Well, the clue here in this data is associated with this plot versus capacity factor. Capacity factor essentially means how often the battery is in use. Okay, how often is it in use? So low capacity factor means that you use it for a couple of hours here, you wait a long time before you use it again. So maybe you charge it one day and then a week later you discharge it. That's a low capacity factor. A high capacity factor would be something like you charge it one day and then you discharge it in the evening. And you can see here that the low capacity factor data all has the lowest efficiency. And we know this is a fundamental phenomenon that batteries cannot avoid, self-discharge. It's because you have the chemicals that are storing the electricity in intimate contact with the electrodes, which are the electrochemical conversion units. And when they are in this intimate contact, there is no avoiding some leakage current. So with this self-discharge, batteries end up being not as efficient as hydrogen energy storage for long duration storage because of self-discharge. Now, one of the things that we at UCI have historically done is to create dynamic models and dynamic physical models. I'm going to talk a little bit more about those later. But one of the things that we applied this to a long time ago, starting in the late 2000s, was the dynamics of Texas wind. And we picked Texas wind because at the time it was causing some grid instabilities where they had to shut down some of the Texas wind farms on some occasions. And they were experiencing negative prices there because of some of these dynamics of wind power. And so we built a model gathering the data from Texas wind farm, as you see it here in the green. This is showing this data for a week-long period in October. Okay, so you can see the green data for the wind power. And we garnered data from an adjacent community that's shown in the magenta color here, going up and down. This is the demand of electricity from the adjacent community. Okay, and then whenever the wind power was available in excess, we would put that wind power into an electrolyzer and stuff that hydrogen into an adjacent salt cavern. Okay, and we modeled the dynamics, physical dynamics of the salt cavern too. And then whenever the wind power was available in deficit, we would take that hydrogen out of the salt cavern, put it through a fuel cell, and meet that power demand of the adjacent community. So here you can see a week-long worth simulation of this Texas wind farm complemented by hydrogen energy storage with the hydrogen stored in a salt cavern. When we were doing this research, there was no hydrogen storage system that was built anywhere in the world that used a salt cavern. But interestingly, in the last 5 years, 2 salt caverns have become operational, fully operational in Texas. Now, they aren't storing renewable hydrogen, unfortunately, but they are proving that salt cavern storage is a viable and very low leakage means of storing hydrogen. Anyways, continuing with this paper, we modeled the dynamics of the storage system, this salt cavern, right? And we looked at the physics of the pressure dynamics and temperature dynamics, which could stay within these maximum and minimum ranges, shown here again for this week in October. And the weekly and hourly dynamics were well handled by this salt cavern. And then what you see here is a whole annual simulation result for this wind farm and community. And what you can see is that wind power is available in excess in November, December, January, February, March, and April. And that's why the pressure keeps building up in these months. And then it seasonally gives that energy back to the community, mostly in July, August, and September. So you can see that this single salt cavern storage is able to handle hour by hour, day by day, weekly, and even seasonal amounts of energy storage. But what if we don't have a salt cavern? Well, that's the situation that we have in California. We don't have a salt cavern. But we do have something quite massive that is underground, just like those salt caverns. And it's the gas system. And another feature of the gas system is not only that it has underground storage, but it also is an ubiquitous transmission and distribution system. Not only is it ubiquitous, but it's also widely available. The Gas Technology Institute, I'm highlighting it here. Gas Technology Institute in 2018 did a service reliability of all gas systems throughout the United States and found that these gas systems are 5 nines available. That means that 99.999% of the time you have gas service. So this is another reason why we should use something like this. I suggest converting it to a renewable hydrogen transmission and distribution and storage system. We should use something like this to make our 100% renewable system in the future. And if you look at the magnitude that we have just here in Southern California, it's equivalent to 13 terawatt hours of electricity storage. That's worth $2.6 trillion in DOE future battery costs. Even if we inject only 5% hydrogen into this natural gas system, which I suggest we could do almost immediately, got to convince our gas company to do that, it would be extremely valuable in the short term. Why do I say that? We could then begin to install massive amounts of sun and wind power that today are not being installed because they are competing with other sun and wind, and the electric grid can't manage it yet. So this is very important. We have to, pretty soon, adopt a standard for injecting hydrogen into the natural gas grid because it's so valuable as a massive energy resource. Okay, $130 billion. Those numbers are really big. So I wanted to compare them to something that you might be more familiar with, or that others might be more familiar with here in this audience. So if we were to send the entire population of Orange County, more than 2.2 million, to 4 years of school at UC Irvine, it would only cost $39 billion. A lot less than the worth of this 5% storage of hydrogen in a natural gas system would be to the grid. We could send them to all University of California schools okay, all the current students, okay, to 4 years continuously at $4.7 billion. We can make tuition free throughout the entire state of California, all University of California schools for just the interest off of this valuable of a battery, this valuable of an energy storage system. It's because it's so massive that even injecting only at 5%, we end up having a lot of energy storage. And the reliability of this has been proven through all kinds of natural disasters. We had the wildfires that led to widespread power outages in San Diego in 2011. And there was gas delivery to many fuel cell systems during that time period that ran straight through it. Winter Storm Alfred, Hurricane Sandy, California earthquakes in Napa here, data center outages in Utah, Hurricane Joaquin, the Napa fire, Japanese super typhoons, Manhattan blackouts, all of these are proven cases of the gas system underground able to provide gas to fuel cell installations that continuously operated. And in current circumstances here in California, where we have wildfires causing outages, where we have public safety power shutoffs, I think it's unconscionable that we should not think that we need to keep a system like this and transform this kind of system together with the electric grid to achieve our 100% renewable policy goals. And we did another analysis just to see how big the effect could be if we not only first mixed this 5%, but what happens if we piecewise convert this to pure hydrogen? So we developed a pipeline simulation model, a grid storage, underground storage model, and then use of those storage facilities and pipelines to move renewable hydrogen around. And the pipes that we simulated are those that go through here, the California-Arizona border. And the idea here is that we could close the valves right here at the border, and we could install a 20-mile by 20-mile square of solar here and not build any transmission lines. Okay, we're not going to build any transmission lines. We're just going to put an electrolyzer next to it, and we're going to use these now hydrogen pipes, okay, to deliver this solar energy to all the end uses that it would otherwise go to, okay, but dispatching it now using existing resources. So again, we're just going to convert all these pipelines to hydrogen, and then we're going to use it in the storage facilities and in the gas plants that are here. How much of a contribution would this make? Well, we simulated the dynamics throughout the whole year. And of course, you can see that every day the pressure goes up and then comes down as the sun is up and making the hydrogen and pumping it into the pipelines. And there are 4 pipelines that we converted to pure hydrogen. And so you got to think about this simulation that we're doing here. We have solar energy and all of the transmission, distribution, and reconversion to electricity included to make zero emissions dispatchable and solar power and storage. So how much of a contribution does this make to our electric demand? Actually, we can meet, without exceeding any of the pressure limits here, 40% of all electric demand with this one project. That is, this one 20 by 20 miles square solar installation and using pure hydrogen in the gas system enables us to go 40 points higher in our zero emissions and renewable content on the grid. Again, this simulation should emphasize for you how massive a resource this is, both in its magnitude, but also in its ability to move it around in society, to move that renewable energy around in society. So I hope that addresses some of the objections that people have with regard to hydrogen. But one of the other objections that people have is that we should try to get higher round trip efficiency. And one of the things that we have historically worked on are solid oxide electrolyzers and fuel cells. And that's why I wanted to spend some time talking about solid oxide electrolyzers and fuel cells. Here you can see some data from our laboratory in which we measured the performance of a proton exchange membrane electrolysis cell and a solid oxide electrolysis cell, both in steam electrolysis, okay, and in co-electrolysis using CO2 and steam, okay. What you can see here is that the kilowatt hours per kilogram, okay, of hydrogen that are being produced is much lower for the solid oxide case, much lower than can be achieved with most proton exchange membrane electrolyzers. So this is one of the ways in which we could improve the efficiency of making renewable hydrogen from those renewable resources. We continue to advance these kinds of technologies in our laboratory, but one of the challenges that they have is that these kinds of systems are not known for their highly dynamic operation. Typically, when you build a solid oxide fuel cell or a solid oxide electrolyzer for that matter, you want them to operate kind of continuously and at steady state. That's not acceptable in this 100% renewable world where we're going to have highly dynamic intermittency associated with the wind and solar power. And so we have historically also made contributions to understanding the dynamic operation of these kinds of fuel cell and electrolysis systems. And the key thing that we have tried to do is to analyze these at a system level, at a system level. And when we analyze these at a system level, we can't resolve all of the geometric features, typically, of the various components. But with fuel cell technology and with heat exchangers and reformers and other things that are a part of these systems, it is important to have some spatial resolution. So the key simplification for most of the dynamic simulation models that we have developed over time has been to have limited, but still some geometric resolution. Then you can actually use these models to resolve some of those geometric features, but then also to simulate like hours and days and weeks and even years of dynamic operation, okay? If you tried to resolve everything, you could only simulate a short period of time. So these are just two examples of like a pretty dramatic simplification of a solid oxide fuel cell with 10 discrete computational nodes. But these are important to resolve because you have different temperature and species concentrations at each one of these nodes, and the dynamics of how that affects both the current that can be produced by the fuel cell and the temperature distribution in this fuel cell are important to resolve. So we can still resolve some of that. This is an example of a 5-node cylindrical coordinates simulation of a reformer module. And that's a reformer module that's pretty complex because it has a depleted steam and fuel flow that comes in the middle here. It mixes with natural gas on this end. It goes through a catalyst bed in an annular reactor that you see here, and a fuel cell exhaust that goes through here to provide some heat for these endothermic reactions. And this provides some heat too. So there's pretty complex heat transfer and even complex flow physics here, but that we can, in a 5 discrete computational nodes, cylindrical coordinates, account for all of that. And then we apply the conservation equations. These are sample dynamic conservation equations from way back in 2003, I guess we started using this kind of an approach. You have to account for all of the species and momentum conservation equations, but then you use the Nernst equation shown here for a carbonate fuel cell under atmospheric pressure operation conditions, and then electrochemical losses and cell voltage computations that you make as a result of these spatially resolved models, and then all the mass conservation equations, which are accounted for dynamically in these models. And then we can use these to do all kinds of simulations that account for all of these physics, okay? And this is from a 2014 paper where we applied it to a solid oxide fuel cell gas turbine system. So you see that the system itself is complex, and you have to resolve that. And then you also have to resolve then the physics of the operation of the fuel cell, the heat exchangers, the oxidizer, the turbine and compressor, et cetera. And you can see here that we are doing this on purpose so that we can operate these things in a dynamic fashion and complement things like the solar and wind power, and to make sure that we do this for safe operating conditions and make these things that people thought could not be dispatched dynamically, highly dynamic, so that they can complement the sun and wind power for the most part. And you can see here there's a lot of things that we were doing in this particular control strategy. We were manipulating inlet guide vanes that you see here in the checked line, okay, this black checked line. But you can see here we were able to keep the efficiency pretty high, okay, over all the dynamic changes. And you can see here the power was changed from 100% full power to 90% full power, down to 70% full power. And all of the temperatures managed well throughout the system. This is the kind of thing that we have done historically and that we continue to do today for making sure that the fuel cell, electrolyzer, and hydrogen energy storage system dynamics can complement sun and wind. And to do that, we've been lately looking a lot at reversible solid oxide systems. So this is an example of a system diagram that we put together where the balance of plant enables this solid oxide cell to operate in both forward and reverse directions, so that we call this a reversible solid oxide cell, reversible solid oxide fuel cell. Those kinds of things I will maybe use interchangeably. Under some circumstances, we may need electric heaters, okay, to support this concept that are shown here. That's what we have here, are two electric heaters that we are showing. In particular, during startup, that's required, but sometimes during dynamic operation, we might need them too. And we've simulated this for complementing 15-minute solar data on a clear summer day. And we showed that if we introduce a high temperature stream from a solar thermal power plant, okay, that has a molten salt, okay, that is connected to it, we can dynamically dispatch this reversible solid oxide system as shown here. Okay, so what we're showing here is that we are providing a power input in the hashed blue line here, and a salt input from the concentrated solar thermal system that is shown here to complement the solar power, okay, that's going into this solid oxide electrolysis cell. And we're showing then that the efficiency of this solid oxide system shown here, okay, is maintained very high on an electric only basis, okay, electric only basis. You can see here, as a matter of fact, it's above 100%, primarily because of that thermal input to the solid oxide system from the concentrated solar salt that's being given to it. And you can see here that we get dynamic dispatch of the hydrogen, but we also can control this system so that we actually can follow the dynamics of the solar and keep all the temperatures and everything in a safe operating condition. We can also do this for a day in which we had a severe cloud come and cover that solar power production in the middle of the day. And we showed here that we could also dynamically dispatch this reversible solid oxide system and keep it within the safe bounds, even under cloudy conditions. Oops. So I'm quite sure that we can improve the round trip efficiency and also dynamically dispatch these kinds of hydrogen energy storage systems so that we can also overcome these other arguments against the use of hydrogen as a comparison to battery energy storage, for example. So I want to end with a couple of thought experiments, or Gdankan experiments, as Einstein called them. The first one is to ask the question, can the LA Long Beach Port complex become zero emissions I'm talking about the whole complex. All the ship traffic in and out, all of the train traffic in and out to its final destination, all of the truck traffic in and out to its final destination. Can the entirety of this port complex be made zero emissions? And in a Gdankan experiment, essentially you want to posit the question and then you want to analyze various aspects of it. And I'm going to analyze some of those aspects. One of the aspects of this is, can we make the container ships zero emissions using battery energy storage or hydrogen and fuel cell technology? The battery energy, what I'm plotting here is the percentage of original cargo space and net tonnage. The tonnage is in the straight lines. The cargo space or volume, right, is in the dotted lines. And you can see that the battery energy storage cases for cargo ships with various number of containers, up to 13,000 containers here at this end of the chart. The battery energy storage cases are shown in red. The gaseous hydrogen storage cases are shown in green, and the liquid hydrogen and fuel cell cases are shown in blue. So what you can see here is that the percentage of original cargo space compared to the original diesel ship, okay, that can be accommodated by the liquid hydrogen plus fuel cell cases is always around 100%. What does that mean? That means that liquid hydrogen plus fuel cell ships can carry exactly the same amount of cargo as their diesel replacements, okay, as the diesels that they replaced. Even if you install gaseous hydrogen storage plus fuel cells onto those ships, the volume will be diminished because the gaseous hydrogen storage tanks take up some of the cargo space. But it only goes down to about 80% of the original cargo, so that these are much more feasible for converting all of those ships to zero emissions. All the hydrogen cases are much more feasible than any of the battery cases, as you can see here. The battery cases are heavy, so they very rarely can carry any of the tonnage. And they also take up a lot of volume. So even in the very best case, only 40% of the original tonnage of this smaller ship can be carried in a battery electric conversion of that ship. Another way to look at this is how far the ships could go if they contained that same tonnage. And again, I'm showing the battery cases in red here and the fuel cell cases in green for the gaseous and in blue for the liquid hydrogen storage. And this is showing the distance that these ships could travel. And again, the percentage of tonnage that they could carry over that distance. And so you can see here that even if you had to go 17,000 nautical miles, more than 90% of the tonnage could be carried that whole distance by all of the fuel cell cases, but not a single battery case could make it that far. And even if it could, for example, only going 14,000 nautical miles, only 10% of the cargo could have been carried. So it's really not feasible to convert container ships or even anything that has this massive payload and long distance that it wants to go using batteries. So again, this is one of those end uses that is much more suited to the zero emissions capabilities of hydrogen and fuel cells. So if we made all of the ships, trains, and trucks through the LA Long Beach port, how much hydrogen will we need? Well, we did that calculation and we determined it's about 8.9 million tons of hydrogen every year that we'd have to make. Wow, can we make that much? Another part of the thought experiment. Well, the first thing we looked at is offshore wind. We know that there are some hurdles to getting offshore wind installed here in California, but it's a pretty enormous resource. As a matter of fact, we just looked at 3 different locations for this offshore wind. And offshore wind costs are coming down. I mean, it's especially coming down with some of the bids that are being promulgated in the Northeast and in Europe. And in some cases, it's coming down to even cost competitiveness with onshore wind. And so we wondered, can we make all of this using this offshore wind? This is one of the farms that we hypothetically installed and then looked at the wind dynamics here and how many wind turbines we could fit into this area. And we determined that we could make 0.3 million to 0.46 million tons every year of hydrogen from this wind farm. In a Southern California wind farm off the coast again here, we could make 3.8 to 4.3 million tons every year. This one wind farm here, it's a pretty massive one, okay, could make almost half of what the port would need. And again, this is to completely make zero emissions, all the traffic through the port. We could also do some onshore wind. The bottom line is that wind power in 3 large wind farms could make all the hydrogen necessary to make the LA Long Beach port completely zero emissions. All the truck traffic, all the train traffic, all the ships, completely zero emissions using the hydrogen vector. Okay, finally, a second thought experiment. As I mentioned earlier, we've been fortunate to work with Microsoft for a long time to consider use of hydrogen and fuel cells and batteries in data centers. And we are currently wondering whether or not we can make data centers 100% renewable and account for all the storage to make them literally reliable, which data centers, of course, require. They require those 5 nines of reliability so that they can make it through the whole year reliably. And we're looking at various cases of sun and wind power being the primary energy inputs and having that primary energy go to the data center, but when it's available in excess to go to batteries, okay? Or when it's available in excess to go to a power to gas and hydrogen storage system, okay? Or to take all of the sun and wind power and to convert it to hydrogen by power to gas. And then instead of having wires going into the data center, to send hydrogen into the data center to power the entirety of it. These are various configurations that we've looked at, but we've also looked at these configurations in different jurisdictions. So for example, Wyoming, Iowa, Virginia, Texas, each of these have different resource dynamics. So they'll have different solar and wind dynamics. And it's important to understand those on a hour by hour and seasonal basis in order to design a reliable data center. And here are some of the assumptions. We have a single axis tracking system that we used for putting into the solar. Here are the cut-in speeds, cut-out speeds of the wind turbines that we assumed we installed. The key thing that's important for you to realize when we do these analyses is I think, very objectively and fairly apply efficiencies in the power to gas case, a 75% efficient electrolyzer, a 55% efficient fuel cell, that are well below those of the battery energy storage system, right? So we have very much lower round trip efficiency in the power to gas cases than we do in the battery cases. We also have to account for what happens to batteries, self-discharge. Here I'm showing we looked at cases between 3 and 9% per month. And we also then have to account for all of the equipment and also the losses associated with the hydrogen storage system. And when we're storing hydrogen at this massive scale, it's most likely going to be also liquid hydrogen storage. And so that requires some liquefaction energy. And also has some boil off. So these are the basic assumptions that we had for this Gdankan experiment. And I'm going to show you a result from just the Wyoming location, which has very specific dynamics, hour by hour of sun and wind. And we can design the system for various features. So for example, we could design this for the most energy going directly to the data center. And that's what's shown on this green line here as a function of the wind percentage. Okay, so here, this is a completely solar case. Here is a completely wind case. Okay, and if we picked a 50-50 mix of sun and wind at this Wyoming location, we would have 81% of the primary energy going to the data center and not needing to be stored. Okay, but that's not the smallest storage system. The smallest storage system, rather, occurs at a different mix of sun and wind. Only 15% wind and 85% sun power leads to the smallest energy storage system, as is shown here with this orange line as a function of all of these design parameters. You could also design for the smallest renewable energy storage capacity. That leads to a case in this particular location of installing all wind power. Okay, so these are various ways in which you can optimize your design. So I'm going to show only one result for an optimal design and optimal mix of sun and wind power for the smallest storage size, and compare the hydrogen case to the battery case. And I'm showing here all of the details of the levelized cost of electricity analysis that we did for the two cases. Okay, so you can see here that the size of the wind and solar that we had to purchase and install in Wyoming is much larger for the hydrogen case than it is for the battery case. This is because we have much lower round trip efficiency in the hydrogen case. Okay, so we're accounting for that. We have to buy an electrolyzer. We have to buy a fuel cell. But the electrolyzer can be independently sized from the fuel cell. Okay, and notice that the megawatt size of the electrolyzer is 100 and the fuel cell is 55 for a 50 megawatt data center, because the fuel cell can be sized just to meet the maximum amount of power that the data center would ever have at deficit. On the other hand, the megawatt hours of battery energy storage that are required to make it through the year have to be purchased as batteries for the battery case. And that's 21,781 megawatt hours are required to make it through the year. We accounted for the operations and maintenance costs. There are fixed and variable operation and maintenance costs associated especially with the fuel cell and electrolyzers, okay? And there are capital costs associated with each of these. And we accounted for the investment charges, the interest rates and everything that have to be accounted for, all of this capital expenditure. And then we also have to account for that in the battery energy storage system case, where you have not only the batteries themselves, but also the power conversion equipment, and then the control systems and everything that goes along with them, including the cooling systems, etc. The bottom line is shown here at the bottom here. This is the levelized cost of electricity in dollars per megawatt hour electric delivered to the data center over a 10-year period. All in for the hydrogen case, buying all the wind power and solar power, buying the electrolyzer, maintaining it, operating it, buying the fuel cell, maintaining it, operating, buying the liquid hydrogen storage and liquefaction equipment and maintaining it and operating it, leads to a levelized cost of electricity of about $120 per megawatt hour, or about 12 cents per kilowatt hour. Now that's pretty high for a commercial rate, but it's not high for a retail rate. We're paying more than that in California today for our own electricity. And remember, this is an all-in purchase of all the renewable power and all the storage system and operating it the entire time for 100% reliable delivery of zero emissions energy to the data center. The battery case, on the other hand, is not possible. Economically, it makes no sense to build a battery this large to store this much electric power for this long a period of time to make a data center reliable. And every single case that we've looked at where we can choose hydrogen for a 100% renewable data center with all the storage and operations costs included is significantly cheaper than the battery cases. And again, it's primarily because of the feature of hydrogen energy storage, where you have separate power and energy scaling. Separate power and energy scaling. We can buy basically a small electrolyzer, small fuel cell, because we size it to the power requirements, the power in and the power out requirements. Every time you need more power in the battery case, you buy more batteries. Every time you need more energy in the battery case, you buy more batteries. And this becomes untenable when you have high renewable penetration, like this 100% renewable case. So as you can see, I am trying to prove to all of you and to the whole world, really, how essential hydrogen is going to be for sustainable energy conversion in the future. And I haven't been able to cover all of the features of hydrogen, but you can see some of them that make it really an essential vector for 100% renewables. It has massive energy storage potential, as I've shown. It also enables rapid fueling and long vehicle range and heavy payload. This is why these ships, okay, can actually be feasibly zero emissions with hydrogen. It can do this seasonal and long duration storage, and it can do many other things, including being a feedstock for chemicals and industry. I couldn't touch upon every one of these, but we wrote a review paper in 2019, Said Manesh et al. I encourage you to read this. It'll give you a few more reasons to become a believer in hydrogen. It's called Hydrogen is Essential for Sustainability. It's in Current Opinion in Electrochemistry. So in summary, we must, and we will, inevitably, increasingly depend upon solar power and its more direct derivatives, these things that Earth naturally replenishes fast on Earth, like wind power. It's going to be inevitable that we will use these. They're the cheapest forms now. The challenge is now, how do we manage those? Okay. And we must manage those in a way that supports air quality goals, but also greenhouse gas and climate goals, energy, environment, and geopolitical sustainability. And interestingly, the ubiquitous nature of sun and wind power and its availability all over the world. Instead of depending upon only the oil-rich nations, we can have everyone rich in the renewable economies of the future. The dynamics of such a future are challenging, and this is one of the things that our program has historically focused upon. They require complementary dispatch of things. They require this massive storage and seasonal storage. And this is where you end up having batteries playing a very big role, hydropower playing a big role. But I think that the largest role in the end is going to be made by power to gas and hydrogen energy storage for some of the reasons that I was able to describe today. And power to gas and hydrogen energy storage, I think, will become indispensable. It's going to become indispensable as a zero emissions fuel and as a storage medium to enable this future. It has some features that you can't engender otherwise. So thank you for your attention.
Thanks. I know we can't have a normal applause right now, but I see a lot of applause symbols popping up on the screen. So thanks for showing us, everybody.
Thank you.
Professor Brouwer, that was an incredible talk. I have absolutely no doubt that there are going to be a whole lot of questions. I know officially that we wrap up at 11:50. We'll keep questions going for a little while. For students
I
enrolled in
went a
this,
little too long, sorry.
that's okay. When students, if some of you who are enrolled in the seminar, if you want a chance to ask a few more questions, I strongly encourage you to join our lunch with Professor Brouwer. You can shoot me an email and I will share the Zoom link with you. So again, I strongly encourage any students who have more questions and want a chance to ask more questions to do that. In the meantime, let's try to take a few questions. Maybe we'll do about five more minutes here, and anybody that has to log off should do so, of course. Please raise your hand in Zoom to show me that you're asking a question, and or include it in a chat line. Either one is fine. Well, let's see, any hands up? I do have one in the chat line. Oh, I see hands up. Okay, Jean, let's get started with you. Please ask your question.
Thank you, Alyssa, and thank you, Dr. Brouwer, for a really interesting presentation. I definitely learned a lot. So my question kind of stems from when you discussed the conversion from using natural gas systems to store hydrogen.
Yeah.
And you mentioned briefly that there's opposition from some of these natural gas companies. So in thinking about how we can actually implement this storage of hydrogen and building that political or social coalition like the natural gas industry has for a long time. I'm just curious to hear about your thoughts there. Do you see the hydrogen storage technologies and this whole field partnering with, for example, the electric systems operator and trying to build some more coalitions around that? So yeah, curious to hear your thoughts on that.
Yeah, there are entities that have been established pretty recently, actually, in the state of California that involve alliances like this. One of the groups that I've been involved with for quite a long time is the California Hydrogen Business Council, and it involves electric utilities and gas utilities, and also a lot of hydrogen companies, hydrogen-related companies. And there's beginning to be a coalition. But it hasn't been strongly established here yet in the state. And I want to suggest that the utilities have been very conservative up to this point and have been more conservative than their European counterparts or their Australian counterparts who have already approved injection standards and are proceeding to do these sorts of things. Now, there's also a legitimate reason for it, and that is that we don't have as high a renewable content yet as some of these European nations. And as a result, we don't have as much of a need yet for the features of hydrogen. But we're going to get there very soon. And that's why we need to start doing these kinds of conversions today so that it's available to us as we go into the future and then do the full conversion over time. A very interesting study is going on in the northern UK where exactly this sort of plan is fully in place. They are already injecting small amounts of hydrogen, and then they have a plan for converting it all to pure hydrogen in a matter of decades. So I think it's going to be inevitable that we will want these features and that hydrogen is going to be one of the only vectors that provides these features. And so we're going to convert our gas system. I think it's inevitable, okay? But it's being the operations people and the safety people are being very conservative yet in the utility framework. Yeah.
Thank you.
Thank you.
We'll take one more question. Cassie.
Hi, yes. Hello, am I coming through clear?
Yes.
Okay, perfect. So I had two questions and hopefully they're they don't take up too much time. But for the electrolyzers for producing the hydrogen, what are you using as your starting material or substrate for that? Is it methane in that case, or is it water or an organic?
No, it's water. It's water. The electrolyzers take the electricity plus water and make hydrogen and oxygen.
Okay.
And so that's how we're making it.
Has any of your colleagues or people that you've worked for thought of using an organic acid and catalyst instead for more facile hydrogen production?
Sure. This sort of thing, people are looking for alternatives, in particular in the proton exchange membrane, electrolysis, and fuel cell communities. They're looking for alternatives to the platinum that's currently the major electrocatalyst that's being used. And of course, platinum is very expensive. And so research like that is super important for this future. So.
Excellent. Yeah, that is what I'm working on. So we will get there.
All right.
And then question 2 is just, is there also work going on with, instead of using hydrogen, using liquid formate as the fuel, because it's easier and it's a liquid, so you don't have to keep it under pressure in a tank, and you can like transfer.
And the formate would come from something like a biofuel production facility as a waste stream or something like that. Is that why you would think that?
Yeah, so I mean, we could potentially take one of those organic acids and then under a carbon dioxide environment, just carbon dioxide captured from biomass or just human waste or whatever it is, and then use it.
So my preference always would be to leave the carbon out of the cycle if possible. Sure. So this is why I really emphasize hydrogen, but there are going to be some circumstances under which we have, let's say, waste streams that we must also manage, and they have carbon in them anyways. And in those kinds of cases, like when we have bio waste and all these kinds of things, then I think it's fine. We have to deal with the carbon then. So that technology is also good and important, but I think it's mostly important as a smaller subset of our renewable future, and mainly to handle the management of waste streams.
Sure. So all of these, the solar, the wind, the hydrogen, fuel cells, electrolyzers, formate
would all got to be the big stuff. Okay. We got to do most of it that way. If we do most of it that way, then it's completely zero emissions on every aspect, right? Zero emissions on the front end, zero emissions on the back end, and we're just recycling water. That's what we're doing. We're recycling water.
Yeah. And then in addition, waste capture to also take all of the things we're also making the carbon like anyway. That makes a lot of sense.
Absolutely.
Thank you so much. Yeah. Great talk. This was wonderful.
Thank you.